All right. Good afternoon, class. Hope you're doing well. Today, what we're going to be doing is finishing up particle physics. So I'm going to do just a really brief review of yesterday. Yesterday we were talking about Feynman diagrams, and Feynman diagrams. The basic component of a Feynman diagram is a vertex, which looks like this. Every vertex has, so this is the vertex right here. Every vertex has a force carrier going in, an arrow going in, an arrow going out, and a force carrier. Okay. Now, for the case of the electron, the force carrier is a photon. It's a gamma. Okay. And then this arrow could be any quark or on with charge. All of the quarks and leptons all of the hi Nihar, hi Spicy Pepper, excuse me, and hi Sofa. So any quark or lepton, with the exception of the neutrino, can emit or absorb a photon. The reason that the neutrinos can't emit or absorb a photon is because they don't have electric charge. Okay. So you have the vertex, and then these three things are called the legs. So you can take the legs and move them around different ways to get different interpretations. So you could, bend it like this, or you could bend it like that. So the interpretation changes depending on how you rotate it. You could bend it like this. As long as you're obeying the rules of a vertex, which is the strong force has, instead of a photon coming out, it has a gluon coming out, which is denoted by G. And then this arrow is representing any quark. Okay? Any quark. So only quarks can emit and absorb gluons. Hi Akshay, hi Rourke, thanks for watching. So today we are going to first of all talk about the weak force. Okay, so this is for the strong force. The weak force has, now the thing about the electromagnetic force and the strong force is that whatever arrow is going into the vertex, it's the same thing coming out. So for example, if this were an electron going in, then an electron comes out. If this were a top quark coming in, then it's a top quark coming out. But the weak force changes the identity of the particle. So it's a little bit trickier. It changes the identity of the particle. Okay. So for example, the weak force could change an up quark into a down quark. So you're changing the type of the particle. The weak force carrier is the line. Now, force carrier that is. Okay. Well, we have to use conservation of charge. So the electric charge in the past, which is on the left side of the diagram, has to equal the electric charge in the future. Okay. So the up quark has a charge of plus 2/3. The down quark has a charge of minus 1/3. Okay. So what that means is what that means is that this thing, whatever this is, has to have a charge of plus 1. Now, why is that? Because in the past, we had a charge of plus 2/3. That means in the future, we have to have a charge of plus 2/3. And 1 minus 1/3 is 2/3. Okay? Now, which of the weak force carriers has a charge of plus 1? Well, there are 3 force carriers for the weak force. There is the W plus, the W minus, and the Z. W plus has a charge of plus 1, W minus has a charge of minus 1, and the Z boson has a charge of 0. So this would have to be the W plus in order to conserve electric charge. If we took this and we reversed it, so what if I had an up quark transforms into a bottom quark, like this? Then the up quark has a charge of plus 2/3. The bottom quark has a charge of minus 1/3. So this thing would have to be this thing would have to have a charge of minus 1, because that means the charge in the past is minus 1/3 and the charge in the future is minus 1/3. The weak force carrier with a charge of minus 1 is the W minus. So this would be the W minus in that case. What if we had an up quark transforms into a top quark? Something like this. If the up quark transforms into a top quark, well, the up quark has a charge of plus 2/3. The top quark has a charge of plus 2/3. Okay, so this thing better have a charge of 0. If it didn't have a charge of 0, then we wouldn't have 2/3 in the past and 2/3 in the future. So this had better be the Z boson, because the Z boson is the one with a charge of 0. Okay, so one of the things that the weak force can do is it can change the flavor of the quark. So when I say the flavor of the quark, it can change an up quark to a down quark, or an up quark to a strange quark, or a charm quark to a top quark. It changes the type of quark. The types of quarks are often called flavors. I don't know why. Actually, one name for the weak force is quantum. It can change a neutrino, or it can change a lepton to its neutrino, or vice versa. Okay, So what it could do, for example, is it could an electron and turn it into an electron neutrino. Now, what force carrier would that have to be? Well, this has a charge of this has a charge of -1. The electron has a charge of -1. The electron neutrino has a charge of 0. So this had better have a charge of -1 in order to make the charge in the past equal to the charge in the future. So this would have to be a W-. Okay. The weak force has to change the lepton into the neutrino for that particular one. So the weak force can't change an electron into, for example, a muon neutrino, because that's not the neutrino for the electron. Okay. So yeah, we can play around with this vertex if I did something like this. And this is an electron. We'll see how I've taken the neutrino arrow and I've turned it against time. So that would be an anti-electron neutrino, and this would still be a W-, and so on. Okay, so I'm going to show you a really important Feynman diagram, which is the Feynman diagram for what is called beta decay. All right, so this is what the Feynman diagram for beta decay looks like. So what we have here is an up quark becomes a down quark. So what force carrier would this be? Well, this would be a if we look at the up quark, it has a charge of +2/3. And if we look at the down quark, it has a charge of -1/3. So in order to conserve charge at the vertex, this would have to be a W+. Okay. Now the W+ is going to make maybe an electron neutrino and an anti-electron. So why didn't I make it an electron and an anti-electron neutrino? The reason, the electron neutrino and the anti-electron, these have a net charge of +1, so it's conserving electric charge. So the net reaction here is an up quark becomes a down quark plus a anti-electron plus an electron neutrino. So this process is called, this would be beta plus decay. All right, beta plus decay. If we also added, maybe we add another up quark and a down quark, up, down, and we add an up quark and a down quark, we can see we start off with up, down, and we end up with down, up, down. Up, down is a proton. Up, down, down is a neutron. So the result of beta plus decay is it transforms a proton into a neutron and then spits out an anti-electron and a neutrino. Okay. This is actually how neutron stars are created. You might have heard of neutron stars before. Neutron stars are made up out of entirely neutrons. So what happened to all the protons? They all turned into neutrons via a process like this. You could also have a Feynman diagram that looks like this, where a down becomes an up. In that case, this would have to be a W minus to conserve electric charge. And then this would be an electron and an anti-electron neutrino. So beta minus decay, what you have is a down quark becomes an up plus an electron plus an anti-electron neutrino. So this has the effect of changing a neutron into a proton. Okay. So beta plus and beta minus decay. Let's see. Yeah, so one thing to remember with beta decay is that you always get a lepton and, for example, an electron and an anti-electron neutrino, or you get an anti-electron and a regular electron neutrino. So they're always going to be, one is going to be a particle and the other one's going to be an antiparticle. Okay. Let's talk about for elementary particle reactions. Okay. So one of the conservation laws, the first one, is that the charge of the reactants has to equal the charge of the products. Okay. A second conservation law is what's called the baryon number of the reactants has to equal the baryon number of the products. So B stands for baryon number. And basically, a quark has a baryon number of plus 1/3. Okay. An antiquark has a baryon number of minus 1/3. And everything else has B equals 0. So baryon number, any type of matter that is made up out of quarks is often called baryonic matter. And so what is, for example, protons and neutrons are called baryons. What would be the baryon number of a neutron, for example? Third plus 1/3 plus 1/3, the baryon number is 1. So a baryon has a baryon number of 1. A third conservation law is called lepton number. So the lepton number of the reactants is equal to the lepton number of the products. So L stands for lepton number. And basically any lepton has a lepton number of plus 1. So for example, electrons, electron neutrinos, muons, muon neutrinos, taus, tau neutrinos. An antilepton has a lepton number of -1, and everything else has a lepton number of 0. Okay. There's one more conservation law for particle physics, and that is called the conservation of strangeness. The strangeness of the reactants this is the weirdest one, equals the strangeness of the products. Okay? If we look at this, S equals strangeness, and this the strange quark has a strangeness of -1. Let me give you an example of we'll do two quick examples and then I'll be done. What I was looking at a reaction of an up quark. Now let's say a down quark becomes a strange quark plus let's say an up quark plus an anti-up quark. So could this reaction happen in nature? Well, what we want to do is we want to go through all the conservation laws and see each of these 4 conservation laws and see if they're all valid. So if we look at the charge, what's the charge of a down quark? The charge of a down quark is -1/3. What's the charge of a strange quark? It is also -1/3. What's the charge of an up quark? It is +2/3. And what is the charge of an anti-up quark? It's -2/3. The baryon number of a strange quark is +1/3. The baryon number of an up quark is +1/3. The baryon number of an anti-up quark is -1/3. So we can see that this works out to 1 in terms of baryon number. If we look at lepton number, well, the only things that have lepton number are electrons, muons, neutrinos, that sort of thing. These are quarks. Quarks have a lepton number equal to 0, so we just have 0 equals 0. So lepton number is conserved. We look at strangeness. What is the strangeness of the left-hand side? A down quark isn't a strange quark, so the initial strangeness is 0. This is a strange quark, which has a strangeness of -1, and these two both have a strangeness of. So if we look at this in terms of strangeness, the strangeness goes from 0 to -1, so that could not happen. So one of the conservation laws is violated. So that means that this could not happen. In nature. Okay. Let's just do one more example. I'm just going to do it at the top of the page here, just so I don't have to do a new page. What if we had a reaction that is, let's say how about a muon and an anti-muon neutrino become a, let's see, a down quark. No, wait, let's say an up quark and an anti-down quark. All right. So let's see, could this happen in nature? Is electric charge conserved? Well, the charge of a muon is -1. The charge of a muon neutrino is 0. The charge of an up quark is +2/3. Actually, let's make this an anti-down, an anti-up and a down. My bad. See, we get -1 equals -1. So we're good in terms of charge. In terms of baryon number, has a baryon number of -1/3. A down has a baryon number of +1/3. So you can see we have 0 equals 0. So baryon number is conserved. In terms of lepton number, a muon has a lepton number of 1. An anti-electron or an anti-neutrino has a lepton number of -1. And both of these, neither of these are leptons, so they both have a lepton number of 0. So you can see we have 0 equals 0. So this could happen in terms of lepton number. And in terms of strangeness, there are no strange quarks in this reaction, so it's just 0 equals 0. So strangeness is conserved. So this could happen. All the conservation laws are satisfied. So that's my lesson for today. I hope you learned something, and I hope you have a wonderful rest of the day. Bye.